Welcome back to Advent of Code 2024, day 24. Hello, DJ. Looks like we're spelling out the number 10. We can't be sure until tomorrow. Right. The problem released like 20 minutes ago, I think. Day 24, crossed wires. You and the historians arrive at the edge of a large grove. I'm sure it was a snake, maybe not. Hey, First Opus. Large grove is this one. Oh, it was like a game of life type thing. Oh, looks like this is going to be like a cellular automata type thing. Cool. Somewhere in the jungle. After the last incident, the elves installed a small device that monitors the fruit. While the historians search the grove, one of them asks if you can take a look at the monitoring device. Apparently, it's been malfunctioning recently. Malfunctioning. Tricky word. The device seems to be trying to produce a number through some Boolean logic gates. Each gate has 2 inputs and 1 output. The gates all operate on values that are either true or false. And gates... Okay, I know what these are. Gates wait until both inputs are received before producing output. Wires can carry 0, 1, or nothing. Alright. There are no loops. Once a gate has determined its output, the output will not change until the whole system is reset. Each wire is connected to at most 1 gate output, but can be connected to many gate inputs. Rather than risk getting shocked while tinkering with the live system, you write down all of the gate connections and the initial wire values. Alright, so these are the initial values. Because gates wait for inputs, some wires need to start with a value as inputs to the entire system. Alright. First section specifies these values. Yeah, okay. All of the gates and the wires connected to them. Alright, First Opus, good luck. Alright, seems clear enough. In this example, simulating these gates eventually causes 0 to appear on the wire Z00. Ultimately, the system is trying to produce a number by combining the bits on all wires starting with the Z. Alright. After waiting for values on all wires starting with Z, the wires in this system have the following values. Combining the bits from all wires starting with Z produces the binary number, blah blah blah. Converting this number to the decimal produces 2024. Alright. So, I mean, you can sort of build a... Alright. I think we can just have like a while loop that's waiting for the Z's to be done and just keep going through these in order. Like, ideally, you would process this in a topological order. I don't know. We'll see what's quicker. So this will form like a... There is a topological order for this, otherwise it wouldn't complete. but can't be bothered to calculate that right now, unless we need it. So okay. Okay, so I suppose we should use regex, really. So we want initial values and do we just want okay, so we'll have a gates, a list of gates, and we want wires, and that can be a hash map. So wires will be 0, 1, or not exist at all. Gates will just be a list for now. If we need to sort them into topological order, we can do that, but there's not that many, so we probably don't need to. How many? We probably want to know the names of all the wires as well, so we could keep track of that when we see. When we see them. All right, let's get the regex. So we want import the all right, so we've got hang on, so pattern 1 equals, it would just be like, so it would be it's always 3 characters, right? So it's I need the cheat sheet. But this cheat sheet doesn't even fully specify. So word character, does that include numbers? Alright, let me look at this. Okay, yeah, word character includes numbers. So basically we want so it'd be word character, word character, And then we've got colon, space, and then a single digit. And we want parentheses, right? So and then so pattern 2 equals, it's gonna be like be word character, word character, word character. And then space, and then we've got, let's just say W plus. You could specify 2 to 3, but this is good enough. And then, in fact, that's strictly letters, so could actually say it's capital D. That's non-digits, basically. And then word characters again. And then word characters again. So there's 4 capture groups here. Alright, for lining. If, alright, so we want if line dot strip dot I gotta look, where did I do this before? 15? Oh, I just gotta search through all these. 14. We'll just look at the imports, then we'll, okay, import RE. RE.match, so it's like this. Alright. So be, so if, so if RE dot RE.match pattern 1 line let's say tuple top equals what am I trying to do here? Okay, yeah, just do it like this. If re.match pattern 1 to line.strip, then we want wire value equals that doc groups. Let me see if this works. So that just unpack it. Yeah, okay. wire, wires, wire equals int val. Okay. Why is it indenting? I didn't tell you to do that. Oh, it did. It copied. No, it shouldn't have indented. All right. Else elif ri.match pattern 2. Then we want wire 1, wire 2, wire 3, basically. Wire 1. Wait, it's going to be wire 1, operator, op, wire 2, wire 3. That. So we just want to store those in a tuple or something and then deal with it later, right? Or just think how we, what is the, okay, yeah, just do that. So we want gates.append probably stick it in a set. That way we can delete things that we've actually used. Efficiently. Gates.add yeah, just do it like a tuple. But we'll do it wire 1, wire 2, the op, and then the results like that. Okay. Alright, that took a long time. Regex always makes me think twice, think 3 times. Alright, so let me just print gates. So the idea is do we want, so there could be traps here. There could be wires which never actually activate. So we could be waiting forever if we wait for those. So we only want to wait until all wires starting with Z, because that's the guarantee, that all wires starting with Z will activate. So should we just say all all right, let's just do this. We say these three wires mentioned here, they could already have values, they might not. So let's just say for W in wire 1, wire 2, wire 3, if W not in wires, because they might already be in there and have a value, wires W equals none, right? So make sure that we know we have knowledge of all wires. That should give us the full list of wires. So let's try this now. So we should have some nones. Yeah. Okay, so we know all wires. Alright, so the plan is while there is any Z wire that still has a none value. So while any W dot starts with Z and wires W is none for W in wires. We'll just go through the gates and in linear order. Just do that. I think the numbers are small enough. So for basically do this for gate in gates, that equals gate so we say if wire 1 is not none and wire 2 is not none, wait, okay, first of all, if wire 3 is already done, this gate is pointless, so we could just say can you just remove the gate from the gates while we're iterating over it? I don't think they'll let us do that, but we could delete them at the end. We'll try gates.remove gate. Continue. If wire 1 is not none and wire 2 is not none, alright, so basically got 3 conditions. It's and or XOR, right? If op is and wire so wires through wire 3 equals wire 1 and that applies to, yeah, if it's just 1 digit, yeah, that will work. It's wire 2 elif. All right, so that's so elif op is or. It will be this. Elif op is zor. It will be that. And then gates dot remove. If we're not allowed to modify gates, then we could just write them to a queue, and then at the end we delete all the ones that should be removed. Let's see if that runs. Set change size during iteration. Okay, so we want to say to remove equals set. Like, this would also be what you use to see if you finish iteration, because there's no more gates to remove. Because there could be gates that never come into play. But then you might be nice and not have those, but you never know. To remove, okay, so you go through all the gates, one pass through all the gates, and then we say for gate in to move gates dot remove gate. This avoids us using, because if we used a list, it would use more time to shift everything in memory. So we say to remove. Why is this a set? We'll just make it a list. To remove dot append gate to remove dot append gate. All right. Let's see if that runs. Okay, and then finally, what is it we wanted? What decimal number does it output on the wires starting with Z? Okay. So we want to take all the Zs. Okay. For W in sorted it's gonna be wire for wire in wires if wire dot starts with Z, and if we do it in sorted order, we'll start from Z00 and go upwards. Say num equals not dot and wires W, and then we want bind num equals dot join reversed. So we're going to reverse them. And then print and you'd have to add 0b to that. Print how do you do this again? Int of bind num 2. Sequence item 0, expect a string. Oh yeah. That. Correct. Alright, after inspecting the monitoring device more closely, you determine that the system you're simulating is trying to add 2 binary numbers. Specifically, it is treating the bits on Y as starting with X as one binary number, treating the bits on Y as starting with Y as a second binary number, and then attempting to add those 2 numbers together. The output of this operation is produced as a binary number on the Y as starting with Z. In all 3 cases, Y00 is the least significant bit. Okay. So we get an X, a Y, and a Z. So if we do this, we should get those numbers. The initial values for the Y's in your puzzle input represent just one instance of a pair of numbers that sum to the wrong value. What? Ultimately, any 2 binary numbers provided as input should be handled correctly. That is, for any combination of bits on wires starting with X and wires starting with Y, the sum of the 2 numbers those bits represent should be produced as a binary number on the wires starting with Z. I'm lost. What the fuck? The sum of those 2 numbers those bits represent should be produced as a binary number on the wires starting with Z. For example, if you have an addition system with 4 X wires, 4 Y wires, and 5 Z wires, you should be able to supply any 4-bit number on the X wires, any 4-bit number on the Y numbers, and eventually find the sum of those 2 numbers as a 5-bit number on the Z wires. One of the ways you could provide numbers to such a system would be to pass 1, 1 on the X wires and 1, 3 on the Y wires. If the system were working correctly, then after all gates are finished processing, you should find 24 on the Z wires. Unfortunately, your actual system needs to add numbers with many more bits and therefore has many more wires. Based on forensic analysis of scuff marks and scratches on the device, you can tell that there are exactly 4 pairs of gates whose output wires have been swapped. A gate can only be in at most one such pair. No gate's output was swapped multiple times. Alright. For example, the system below is supposed to... I'm not really following. We'll just read it through and then read it through a billion more times, I guess. For example, the system below is supposed to find the bitwise AND of the 6-bit number on X00 through X05 and the 6-bit number on Y00 through Y05, and then write the result as a 6-bit number on Z00 through Z05. All right. However, in this example, 2 pairs of gates have had their output wires swapped, causing the system to produce wrong answers. All right, so we don't really need to... Okay, so we don't care too much about this. We don't care about the initial values right now. So, basically 4 of these gates. So this is whatever this is doing, it's supposed to result in X and what did they say? X plus Y. Z is supposed to reflect X plus Y. But it doesn't, because there are 4 wrong gates. 4 pairs of gates whose output wires have been swapped. Okay. Fine. 2 pairs of gates have outputs that are involved in a swap. By sorting their output wires names and joining them with commas, the list of wires involved in swaps is that. If you were to determine that you need to swap output wires AAA with E, blah, 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 your answer would be... So you find all the output wires which need swapping and put them in a string. Okay, fine. Your system of gates and wires has 4 pairs of gates which need their output wires swapped. 8 wires in total. To determine which 4 pairs of gates need their outputs swapped so that your system correctly performs addition. Bloody hell. Alright. What do you get if you sort the names of these 8 wires involved in a swap and then join those names with commas? All right. Hello, Dira. Are you doing Advent of Code as well? This looks kind of nasty. So we know how to run the system once. So, like, the obvious approach would be to just iterate over all possible swaps and just run the whole system again. Like, do we think that would take forever? The thing is, the gates, this thing about topological sort for the gates might come into play, but then again, it might not. I mean, the number of gates is not that big. How many gates have we got? Let's have a look. So it's 92 to 313, so it's like 200 gates. And this algorithm we're using, where we just go through the gates over and over again until everything's done, is kind of slow, but it works. Alright, we can just try it then. So we say this whole method is one execution, and if we're looking for 4 swaps, then we need to find 8. Oh man. It's gonna run like 1.6 billion iterations, right? Yeah, that's not... If I just swap wires willy-nilly, that's not gonna get me there. Can we work out if even one swap is in the right direction? I don't really see... So there are some swaps which might result in like the system never terminating, or yeah, we also need to check if it'll terminate, because we might make it impossible to terminate. So if we make a single pass through the gates and don't find any new things to change, then we've failed, and that's... we have to detect that. So that will be detected when this is empty. So, okay. So we know one way of doing this, but it'll be too slow. Now, okay, so we know early on if we've... whenever we find a Z0 and an X0 and Y0 and so on, we can check if they add up correctly and terminate early. But we're still iterating through many different swaps, so we need to... How many Zs are there? Let me print the binary number as well. That's the binary number. That's how many Zs there are. So it looks like we want to find individual swaps which because it's addition, we have a carry. That makes it even more confusing, because then we can't break this down into... I'm just reading through the description again. So it is binary. It's an addition of binary two binary numbers. Okay. Let's see what we actually have right now. So what we've got right now, let's just wrap this up as a method, I suppose. So this is one iteration. I'm going to say define see, the topological sort idea now doesn't even quite work because it will be a different topological sort depending on after the swaps take place. But I mean, that can still be done before this stage. That's not a big deal. The big deal is the number of pairs we need to iterate over. All right, so let's say define get, I don't know, XYZ for a given set of, well, all right, just with no input for now. All right, so while well, it will be wires, won't it? Okay. While any while W0 in XYZ. So while there's any XYZ that's still none, we do this. Wires and gates. So we give it a set of wires, and a set of gates. We don't have to give it a set of wires. We're not changing the initial values. So wires, let's say all right. Let's just call this wire map or something. All right, wire map. So whenever we use this, we have to change this. Those. We don't even need to supply it. We just say wire map equals wires.copy. That should, because those are like primitive values, it should just give us a clean copy of wires. Gates is the only thing we do need to supply because we're telling it the new set of gates to use. All right, so that's one iteration. While any XYZs need And then we've got, we can say, we do need to do this for x, y, and z. So we say x is that for w. If y, we don't need to do that. Just do y 0 equals z or x. So then we do just say x num or x bits, I don't know. So x equals, just do this, int that 2. That should be y map. All right. So we do this for y as well. Z. Y. 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 And Z. Right, and then we return x, y, z, I guess. All right, and then one last check. We want to check for infinite loop. Well, if the system just never resolves. So in that case, so if to remove, there's nothing to remove. That means the system we did so this hasn't. This is still. There's still nuns here, but there was nothing done here. So that means there's no way to get x, y, and z. So turn up, I suppose. All right. Okay, so part 1. Let's call this init gates. Okay, so part 1 we do x, y, z x, y, z equals get xyz of, let's say, init gates.copy. In fact, we should just say no, that's fine. Print x, y, z. All right, I just want to see if non-iterable none type. We've got a none. If not, so we got none here. If not, to remove. So if this is empty, it's not working now. We broke it somehow. Also, I need another coffee. This is a bit of a mess. All right. Well. Let me just see what's going on here. So we remove those and then wire map, see what's happening here. So we filled it in. Oh, fuck's sake. This is why you should use refactor. I said that yesterday, didn't I? Made the same mistake. But it looks okay now. Let's just make sure we've got wires floating about anywhere. Run that. X, Y, Z. And is that the same Z we had? 880. Yeah, okay, so that is one iteration. And let's do X plus Y, Z. Let's compare the two on different lines. So that is X plus Y, and that is Z. Interesting, so they're quite close. So, do we think it'll be a case of swapping to get closer? But it's not, that wouldn't... So I'm thinking maybe we actually just have to look at this whole get graph is out and look at the actual graph of gates and figure out what's going on. So a swap is basically taking like the subtree from a gate and swapping it with the subtree of another gate. Now, hopefully there are no feedback loops in this graph. There shouldn't be. No, because... that does, well... I mean, there can be cycles, definitely. I don't know. I mean, we might not need to look at the structure of it yet. Let's see if we can figure out stuff. Well, we're actually... It's a case of getting the digits to match up as well. So the first place where they go wrong is here. So whatever happens to Z, whatever that Z is, we need to correct it. And then over here, like we don't, there's carries, so we can't always okay, so it looks like there's one so there's a bad wire here, bad wire here. That looks like it's part of the same bad wire in X and Y. Looks like there's one bad wire here. So is it literally just 4 mistakes and hang on. We just want to find, like, start off with finding a swap to make this digit correct at the on the right hand side, and just repeat. Like, that shouldn't necessarily solve it, because a swap could do anything, really. But it looks like the structure of this gate tree is actually kind of nice. And it may not have any wires going back and stuff like that, so maybe that's what we do. Okay, so basically we've got we know where we don't actually need the ints either. We just need the binary. So z equals that'll be dot join reversed. That. Let's do that. Okay, we just need those. Actually, that's... Oh, no, we're not doing binary now. Actually... Yeah, that's fine. But we need X, Y, and Z here. So I think it's a case of we get X Y and Z and find the first bit which doesn't add to Z. Let's try this approach. I don't know if this is necessarily correct, but it might be just a case of finding the 4 swaps almost manually. We don't need to do it manually, but we can kind of adjust the code manually each time we find one. How long have I been going? Only an hour. Okay, not too bad. We're not broken our record yet of like 4 hours or something. So we've got this. So we want to say so we want to find the place where they differ, right? So for I in range length of Z if So it's going to be x minus I minus 1. So we're basically doing a XOR here. We don't care about the carry. Is not equal to z minus I minus 1. Break. So this finds the I. So let's just verify that. These are strings. All right, just say one. No. Oh, no, this is not how we do it. What am I doing? For I in range, we just want to just take the right-hand section and add it. Just add it. So we want to do if so it's going to be int of b plus x let's just say x tail equals x, so it's going to be minus I minus 1 onwards. Suppose we can add 0b to that because that's now a binary string. Y tail equals that. Alright, so the expected Z tail equals so it's going to be int of xtail2 plus int of ytail2. So we add them together. But then we will just want to take the I. We want to cut off the if there's a carry, we want to ignore that. We just want to take the final I digits. So it's gonna be just turn that back to binary and take those digits. If not z dot, is there like an ends with? Is that a thing? Expected tail break. Is that the thing? It is, okay. So we're saying 8 is where they differ. So 1 plus 1 is 0, carry the 1. So we're saying 6, 7, 8. So we're saying that. So that's, let's just do this manually. That is X. Hang on, we're saying, yeah, 0, 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 2, 3, 4, 5, 6, 7, 8. Why am I doing it this way? Do I not just want... No, because we're interested in which digit is wrong in one of these. That's... one of these numbers, X or Y. So we're saying that plus that should equal that. 0. Yeah. Okay, so that and that sum to that. Then we've got 1 and 0 gives 1, 0 and 1 gives 1, 1 and 1 gives 0, carry the 1, 1, and the carry should equal 0. That's where it fails. Okay. So what have we done? We've got a way of finding where the first failure point is. So the idea is, if it's as simple as a swap corrects an error, then is that what we want to do? Let's try this anyway. So we're saying give me a pair which wait, this is not part 1. Part 1 was print Z, so it was like int 0 b plus Z 2. That was part 1. Don't interfere with part 1. All right. Leading decimal integer literals are not permitted using what? Oh yeah, I don't know. Okay, get rid of that. Invalid literal for int with base 10. What? Oh, that bracket is wrong. Okay, yeah, that's still right. Okay, don't interfere with that. Part 2. Alright, so let's wrap this up as a method. This is basically saying define get first wrong bit. Hang on, let me look at the description again. Alright, I've slightly misunderstood this. This shouldn't just work for the initial values of the y, it should work for any initial y values. That makes it easier, not harder. Because we get control over the wires. Oh! So we can like set them to 0 initially. Alright. Alright then. That makes it easier, so we get control over the wires. So... So x, and this is wrong as well. This we don't care about. Yeah, let's do that. We don't care about. We set x and y. So we shouldn't be doing this at all. We don't get back x and y. We set them, right? Yes. I get it now. All right. So that's actually, it's just actually simpler. So z is just that. Okay. We set x. All right. So part 1, leave that alone. Z equals get initial. All right. So we need to supply basically x and y, and those get fed into the initial wires. So let's refactor this. I'm gonna do refactor for the first time. Init wires. Okay. Okay, so wire map equals init wires.copy. We're given x and y as binary strings, let's say. So but if we want to leave it x and y alone, then let's just do this for now. X equals none, y equals none. Make sure we still get the right answer here. Yeah, we're messing everything up. Hang on. Just all right, it doesn't matter, we're not using this right now. Okay. All right, I see. All right, so this method, hang on. Punch. almost 3 p.m. Maybe we can do this quickly now that I've realized that we can control x and y. So if x and y is 0, for instance, then how many x's and y's are there? Let's just find out from the initial input. Num x bits equals. So it's going to be something like this. It's going to be equals sum W. Wait, did they actually say in the description? No, okay, we need to get it from the input. So some W. Why did I write that? Oh yeah, that is that. Okay, so sum W Z equals X and let me show for U in initial wires. We need to know how many bits there are altogether. Print X bits and Y bits. 45. And num Z bits. Right, that's what I was expecting. Okay, fine. All right, so now we want to be able to give an X and a Y. So we say Y map equals initial wires dot copy. If oh, it's only X and Y's that are given, nothing else. Ah. All right. In that case, if X is none and is, what if one is none and the other isn't? We shouldn't allow that. Let's just say X, Y is a pet tuple. You have to give them together or not at all. Alright, if X, Y is none, wire map is initial map, Y is the copy, else wire map equals this. X, Y equals XY. That's going to be given as a tuple. So are we just gonna give the full list of bits as input? Then we don't have to do much logic here. We can just say for I bit in enumerate reversed X. Are you allowed to do that? Enumerate. Oops. For I bit enumerate reverse. Yeah, you can. Wire map. So it's gonna be X plus I plus string I equals int bit. Is that how it's done? Oh, we need to have a 0. Dot left dot pad. How do you do this again? Dot z fill two, and that's wrong. String I dot z fill 2. Yeah, that's right. All right. We have to just verify that that works because I have no idea what I'm doing. All right, so part 2. Let's try y x equals 0, y x y equals 0 0. All right, so we want get x y z using the initial gates, and we want x y is gonna be oh, okay, so we want binary x 2 onwards. We probably want to wrap this up as a method. Define get bind input string for a given like value, let's say b. Return, it's going to basically be this. It'd be like, take the binary, strip off the first 2 characters, and then we need to fill it with zeros until it is of size num x bits. That's the same for x and y. Like, we should really... Well, x and y are the same, so it's okay to do it this way. But what if they weren't? What if they gave us different numbers for x and y? Do we want to be really precise? Yeah, go on then. Let's call it get bin x, x, turn that, get bin y, y, that. Alright, so get bin x of x, get bin y, y. And see what we get. So we've given 0 and 0. Now, this logic should be in the method anyway. We'll do that later. 0 and 0 gives us... get export. Okay, so it's correctly put all the zeros in there. Why didn't we get a result? Print. Are there no Z bits? No, there should be. We should be getting zeros. If Z is if Z is just zeros. So if it's a none, we'll see a none. We didn't get that. What is this? Is this an empty string? Did it dot join reversed? No, it should be zeros. There shouldn't be any way of returning an empty string. What's happened here? Okay, we trust that. Alright, dear Jay. This is a bit of a nasty problem. I don't even really see what the whether I have a final solution yet, but adding 0 to 0 and seeing what we get might tell us something. What? Am I getting an empty print? Alright, first of all, to take this stuff into the method, I don't know why we put it here. So we take binary value of that, then do that to turn it into the binary string, and then put those into the map. do the same thing here. Right, so we should just be able to get that with 0, 0. What's going on here? Do I have a return somewhere? It's not hitting that. What is going on? So do we get to the end here? We get here. And then we return Z. So Z is an empty string? Reversed Z bits. Z bits is that. The W in sorted wire map. Oh god. Because we don't know any other wires. Alright, so what we need is that if x, y is none, we then take the wire map and replace them. Cannot unpack non-iterable non-type object. What? If xy is none, is not none. Okay. Wire map is initwires.copy. What is going on here? Alright, just show me wire map. So that's that. And then these are all nuns. That's the first one's correct. The second one. Oh, yeah, we were supposed to use that. There we go. All right. All right. Okay, we've got what I was expecting it would look like. All right. So that is Z for X and Y is 0. Good. So far, so good. It works for zeros. Now what? Let's try X is 1. Alright, we fail for that. So I'm gonna go for lunch. So this might be the first ever Advent of Code this month where I don't finish in one sitting. But Yeah, probably will do that. And I'll have a think about what we do next. I haven't even really sat down and thought what my solution is going to be. I just wanted to code something which actually computes the wires and does that. It's not even that efficient because I don't like this repeated passing through gates and removing them and so on, but it works, and I don't think we really need to. I think it's really a case of clever use of X's and Y's to see where the problems are and fix them. Basically, you need to do that 4 times to find the 4 problem points. How would you work out what the pairs are? The pairs could, the swaps could be anything. You could swap like JKV with Z29 here. But like we have it's like when X is 1 and Y is 0, we get Z is 0. That's just 1 bit wrong. So can we just find a swap? Find all swaps that would fix this one calculation. It might be that might get us somewhere. How many swaps do we do altogether? 4. That's not many. If we could just find all 4 manually, I'd just call it a day. Wait, so what happens if we do 0 and 1? We get 0. Interesting. And if we get 1 and 1, we get zeros. Just some numbers. Hang on. Why is it always 0? So we could. How do we get the initial? Oh, I'm putting zeros here. Whoops. Alright, so it was... alright, go back, do this. 1 and 0. Adds correctly. 1 and 1. Alright. Okay. Well... Now, it seems sort of correct, but we want to... So somewhere, then okay, so if we keep Y as 0, and just add these, what's 2 to the power of 45? Can we actually try all X values or just... Yeah, it's too big. But we're not going. We don't need to try all X values. We can just try all powers of 2, for example. Let's try that. So for how in range I don't know, 44 for power in range 44, x equals 2 to the power of p z equals that, just use that, print z. All right, well, we can just print them for now. So it's x and 0, x equals 2 to the power of p. All right, so the first place where they go wrong, we can see is here and here, here, here. Interesting. 40. Wait, we can go to 45, can't we? Yeah, all right. So is it just a case of finding swaps that will fix this? Try that. All right, let's just try it. Maybe it's actually simpler than that. I was worried it would be much more complex because it's like a complex system, but maybe it's not actually that complex. Let's do. So how do we do a swap? So we want to say for I in range length of gates, init gates, for j in range I plus 1, length of init gates. We're going to swap I with j. So, but that means we need to just swap the outputs. So say let's define get num mistakes. So for p in range 45, do that, z equals that, and then we want if z, so we want int of 0b plus z2 is not equal to x result plus equal 1. So let's just see, how many mistakes do we have here? Print get num mistakes return result. 4, exactly 4. Interesting. For I in range, length indicates. For RJ in range. So let's just see. If swaps are independent, then it's actually much easier. We don't have to do all swaps, find all combinations of swaps. Just find each swap individually. I don't know. Just try it and see. For I in range that, for J in range that. So a swap means swapped gates equals init gates dot copy. So we want, so the order is maintained in these things, right? Gates. Or maybe we should, it's a set. So we should actually swap based on the actual gate. All right. So outputs are unique, right? What? Yeah, the right hand side is unique because you can't have two gates going to the same one. So it's basically, you're basically swapping two wire names essentially. So we just want for okay, let's just do this for gate in init gates gate 1 for gate 2 in init gates if gate 1 is the same as gate 2. Skip this one. All right, so we just want to swap the outputs. So gate, new gate 1 is going to be gate, so it's going to be gate 1 0, gate 1 1, gate 1 2, and then we take gate 2 3, right? New gate 2 will be gate 2 0, gate 2 0, gate 2, gate 1 3. So we say swapped gates equals init gates dot copy, but swapped gates dot remove gate 1, swapped gates dot remove gate 2, swapped gates dot add new gate 1, swapped gates dot remove gate 2. That new gate 2. This set data structure isn't the right thing for this. It probably would have made more sense to do a hash map which maps wire names to their Boolean value. expressed by the gate, that basically coincides with the wire map, and that makes for a cleaner way of resolving wires. Doesn't matter. We'll just stick with this for now. And then this swap will literally just be swap the two hash values. All right. So we do that. Got swapped gates. And then we do get num mistakes. If, oh, what am I doing? If get num mistakes. So get num mistakes also needs gates. If get num mistakes with swapped gates is, let's say, less than 4, just print the values. I just want to see what's going on here. We want just print gate 1 and gate 2. I want to see what things got swapped. All right. Get num mistakes. Can only concatenate said. Z is none. Well, if there's a none, then we call that a fail, right? If Z is none, result plus equal 1. Elif. So if it's a none, that means we never actually found the value of Z, but we made things worse. 40. Okay. Get num mistakes. It looks like we're making more mistakes with these swaps. Is there any swap that's actually correcting it? 40. Interesting. Print get num mistakes swapped gates. What's going on here? Print what? We're not getting anything. Print. Oh, why did I do remove here? Oh my god. Still not doing anything. Get num mistakes should always return a number, so that's weird. What? Alright, forget about this. Gate 1 equals gate 2 continues. how result equals 0, p in range. So it doesn't matter what we do here. We should always return a number, right? So get non-mistakes. Stop doing that. Okay. So we're trying all pairs of gates, right? So some of them are. Why did I say 4? Damn it. What was the initial one? Let me do that again. $44. So we didn't find any which reduced the number of mistakes. Wait, 44? All of them are mistakes. Oh yeah, of course. Oh, no, no, no. I don't mean number of cases where it's... Oh, damn it, hang on. What do I mean here? Don't mean number of cases where Z is wrong, because Z's wrong, for sure. We want... Also, the music stopped ages ago. Hello, Quest Opus still going. I can't tell whether it's tough or not, to be honest. I've sort of got hung up on trying to implement these wires, and I'm sort of doing it, and I keep on trying to implement different things, but for all I know, the solution might actually be quite simple. I haven't really thought about solving it. I've just been trying to like see what happens when I set x equals 0 and stuff like that. Finally finished part 1. But what was part 1 again? Oh yeah, part 1 was with just find the value of Z. Yeah, okay. So yeah, part 2 is a bit confusing to interpret the description. I don't think... What was part 1 again? Well, yeah, I mean, well, it's been a while since I did part 1, that's... Alright, I think I gotta go for lunch. I don't wanna... And then I'll come back and continue with this later. I need to eat. But... What was I trying to do here? I was trying all powers of 2 for x, and just seeing... Hang on. Let me look at these again. Alright, so to comment this out. There was something I was trying to count here, and it wasn't mistakes as such, it was... Okay, let me just see what these look like. Print x And this. Can only concatenate string and non-typed string. We're getting nuns? Why are we getting nuns? For P in range, if Z is none, result plus 1 else. Print X. That's not what it looked like before, is it? What is going on here? Oh, I forgot to copy. That's probably what the problem was. It was modifying the gates. Ah, that's what happened. We copy here. The copy should be done in the method. Why didn't I do it that way? I will change it to do that. Let me just see if this fixes it. Okay. So it's correct. There's no mistakes there. No, because I'm not adding them. Four mistakes. That's what I had originally. Okay, now we do this thing again and see if we can do better than 4. Make sure we... Yeah, we are making the copy here. Okay, go. So now it's trying all swaps and seeing if they fix this thing. So we're saying swap Z16 with BKR, Z16 with KBG, KWV with VBR. Now swaps have to be independent, so we can't have these two simultaneously. But this is interesting. So we found swaps which improve the number of mistakes. So that it could, the swaps we need could just be amongst these. We only need 4. Also, I should have printed the... Let me just do this. Start again. I just want to see what is actually, how many mistakes we're getting. 4 is the number of mistakes. So that gets us 3. It could just be a set of these then. We just have to pick 4 of these, but there's more than 4. 4 pairs of gates which need their output wires swapped. Let's just see what we get here and then do something with those. Really need to eat. Like, I don't know if there's just a tiny bit left. Is it just a case of... So we just need to pick 4 of these. And let it run until we find all of them. How long is this going to take? We should probably... Like, why are we getting different numbers now? I guess because the set was just in an arbitrary order. It shouldn't be. It should be the same every time I run it. Did I change something? So we're saying we swap KBG and Z16, RNQ and BKR, Z08 and VBR. These each correct 1 bit, but that could just be a red herring. It could mean nothing. NGF and BKR. So maybe it's time I actually start thinking about how to solve the problem and stop just playing around and seeing what happens. So the problem is we want to so a swap basically means you're swapping the value of a wire with another wire. So this is not entirely helpful because Z is all zeros except for one. Actually, this is quite helpful because we're saying it's interesting that there's exactly 4 mistakes, and they said there's going to be 4 swaps needed. So each swap we do should correct a mistake, right? Like, it's not coincidence that number is 4. But in theory, a swap could do anything. It could increase the number of mistakes, it could decrease it, it could do anything, but it looks like they're sort of independent. So correcting one corrects one mistake. And we've got too many coming here. So anyway, it looks like these pairs could have something to do with it. Like, it's just a case of which ones. So there are, some of them are coming up often. CTV, DVR. Out of order. Alright, I think I'll just go for lunch and come back to this later. If I just plot this in Graphics or something, maybe there'll be something that stands out about this that makes it much simpler. Than I think I'm overcomplicating it, because if I'm probably trying to solve too general a case. I think it's actually much simpler. For example, do any of these appear in multiple gates? Like, is it actually completely independent chains? If it is, then this problem breaks down pretty straightforwardly. Like, look, x38 and y38, 24 and 24, 39, 39, that's interesting. 6, 6, 1 and 1, like there's some regularity here. We're doing things with... that is interesting. Okay, this is way more regular than I realized it was. 18 and 18. So it's always taking the X and the corresponding Y, taking them somewhere, doing something with that, and probably ending up at Z12, for example. So you've got X12, Y12, goes to KQP. KQP goes with HCC. What was HCC? HCC comes from SCK or KMS. I just want to see where these chains came from. That came from 11. Interesting. I should plot this in GraphViz and look at it. I think it's going to be much clearer then. I've been solving a really general case, which I don't think you can do because there could be any amount of complexity here. Alright, I'm going to stop there. I'm going to go have lunch, have a think about it, come back, and next time we'll stop messing around with these loops and stuff and just try to solve this analytically. So, I don't know, I'll be back in maybe an hour or so. Could be longer, depends how I feel. Alright, we didn't finish it yet. Bye bye for now.